Bismillahirrahmanirrahim. Welcome to the class of classical mechanics. In today's lecture, we will discuss the conservation theorem of the linear momentum using the Lagrangian and Hamilton formalism, and also we will discuss the equation of motion of Atwood machine consisting of a single pulley. And in the last topic, we will discuss the derivation of the Lagrange's equation of motion from Hamilton principle. Okay, so derivation law of conservation of linear momentum using Lagrange's and Hamilton formalism. So as we know that Lagrangian being a function of generalized coordinate, generalized velocity and time is equal to the difference of the kinetic and potential energy. So L is equal to T minus U. If you differentiate this Lagrangian with respect to the generalized velocity x dot j. So curly L over curly x dot j, it will become curly T over curly x dot j minus curly U over curly x dot j. So as you know that potential is not a function of velocity, so it means that it's the partial differentiation of the potential energy with respect to generalized velocity is equal to zero. uh, is the potential is a function of position, generalized coordinate or position only. So this equation is reduced to equation number one, and also is the kinetic energy is equal to half mj x dot j square. This is the kinetic energy. X dot j is the generalized velocity of the jth particle. M is its mass. So if you differentiate this kinetic energy with respect to x dot j, so it gives you mj into x dot j, which is equal to the generalized momentum pj. So uh, curly t over curly x dot j is equal to pj, which is the generalized momentum. So equation number one is reduced to curly L over curly x dot j is equal to pj. For curly t over curly x dot j, we write pj. No, also is from the Lagrangian equation of motion, which is equal to d by dt curly L over curly x dot j minus curly L over curly xj is equal to 0. So this is the famous uh, Lagrangian equation of motion where L is the Lagrangian function. So uh, here we can put Pj for curly L over curly x dot j. For this term we can put Pj. And also uh, we can write as this is L, and L is equal to T minus U, but it is differentiating with respect to xj. So it means that T and U also will differentiate with respect to xj. But T is not a function of xj, it is a function of x dot j. It means that curly T over curly x dot j will give you 0, and curly U over curly x will remain. So curly U over curly x, it is basically the potential gradient minus del U, which is equal to the force F. It is the force F in a conservative field. So for this term, we can write force F, or Fj you can write. So here we can write Pj, d by dt, Pj, and here we can write F. So remember this. So it means that when F is equal to 0, so it means that in the absence of an external force, uh, the force will be 0. So it means that d by dt is equal to Pj, which show that P is equal to constant. That is, the change in the momentum with respect to time is equal to 0. It means that momentum remains constant. So we have done another way rather than written in these notes. So we have in fact put F for this term, which is the force. So when force is zero, external force acting on a body is zero. So it means that its momentum is conserved or remains constant. Hence, it can be stated that the generalized momentum conjugate uh, to a cyclic ignorable coordinate is conserved. In fact, in the notes we have done that del L over del Qj is equal to 0 or for Q is equal to x uh, j, and we say that xj is a cyclic coordinate or ignorable coordinate, so curly L over curly xj is equal to 0. So also you can do in this manner, or you can write force for this term, and when force is equal to 0, then it means that this term is equal to also equal to 0, and it shows that pj is equal to constant. So the next topic is the Atwood machine, and we have to find the equation of motion, in fact, the acceleration of this system. So as you know that Atwood machine for a single pulley is consisting of a length of a rope which is connected to two masses M1 and M2 from the ends, and if it can move on a pulley which is fixed, and it can rotate in the horizontal plane. So this is the uh, distance x. So then it will become L minus x. So in fact, these are the coordinates of the two masses. So hence the velocity of the mass 1 will be equal to dx by dt is equal to x dot, and for that mass 2 will be v2 is equal to d by dt L minus 6. So as L remains constant, it is constant, the length which cannot be changed, only x change, so it become minus x dot. You can see that both are equal and in opposite direction. So if one mass come down, the other will go up. So the velocity will be the same, but will be in opposite direction. Hence, the kinetic energy is equal to half m1 x dot square plus half m2 x dot square. So uh, if you take the square of x dot, so it will become positive. So there is no negative. And also the potential energy is equal to minus m1 gx and minus m2 gl minus 6. So minus is for that all the potential energy in a gravitational field are in fact negative. So the negative sign comes from there. So hence, the Hamiltonian function is the sum of the kinetic energy and potential energy. So if you put values of the kinetic energy and potential energy, so it gives you this equation, and you can simplify by taking x dot square divided by 2 from these two terms, from this term and this term. So it will become m1 plus m2, which is equal to the total mass m of the system. And if you multiply m1 plus m2 in the denominator and also multiply in the numerator, so you will have m1 plus m2 into x dot square, which will become momentum. Momentum is equal to mv, or m square v square will become p square. So this is the momentum of p square, and here the mass is in fact m1 plus m2. So we have transformed this equation in terms of the momentum, and these two terms will come as it was before. So hence, as you know that from the canonical equation of motion, that is q dot j is equal to curly h over curly pj. So here q dot j is equal to x dot, and pj is equal to p. So if you differentiate this equation number 3 with respect to p, so we are left with p divided by m1 plus m2, because these two terms has no momentum terms p, so it will become 0, and only for this term we will get p divided by m1 plus m2. So if you differentiate again this with respect to time, so it will become x double dot is equal to p dot divided by m1 plus m2. So remember this equation number 4, and also we have that p dot j from the other canonical equation. from the Hamilton canonical equation, we have P dot J is equal to minus curly H over curly uh, Qj. So for Qj, we have X, and for Pj, we have P. So if you differentiate again this equation number 3 with respect to X, so we have X in these two terms, m1 gx, and in this term, and there is no X in this term, so it will become 0. And the differentiation of this will give you m1g minus m2g. If we can take common term g as, it will become m1 minus m2 into g. So if we compare equation number 5 and equation number 4, this equation, so there is a p dot, and also we have p dot from this equation number 5. So comparing both these two equations, so it gave you x double dot is equal to m1 minus m2 divided by m1 plus m2 into g. So this is x double dot is basically the acceleration of the system, and it depends on the magnitude of the masses. So if m1 is equal to m2, so this term will become 0, and in fact the acceleration will become 0. So it means that there will be no motion, and both masses will have 0 velocity and 0 acceleration. And if m1 is greater than m2, so m1 will go down and m2 will go up. So in similar way, we can have, if m2 is greater than m1, so then m2 will go up and m1 will go down. Equation number 6 represents the equation of motion of an Atwoods machine consisting of a single pulley. Okay, so next is very important, derivation of Lagrangian equation of motion from Hamilton principle. So just as we have done that, how we can derive the Newton law from the Lagrangian equation, in fact the Newtonian formalism from the Lagrangian formalism. So in this topic, we can show that how the Lagrangian formalism can be derived from the Hamilton formalism. So as we know that if a system is transferred from one state to another state, from T1 to a state of T2, so we have Hamilton principle, that is delta integral of L dt is equal to 0 from T1 to T2. This is the famous Hamilton principle. So here uh, we can take as this delta can operate on this term. So this is the product of two term L and dt. So it means that just the differential of the product of two terms, we can apply this delta on L, and then in the next term we can apply this delta on dt. So this delta into dt is equal to 0, because for all the paths the change in time rate is 0. If we go from different path from T1 to T2, so there are 3 paths, there may be more parts, more paths. So there is no change in the time interval. So we have this term equal to 0. So we are left with only one terms. And remember this equation number 2. So no is, we know that the Lagrangian being a function of the generalized coordinate and generalized velocity and time, the differential of L in terms of delta, we can write this is the famous equation we have done several times in the last in the previous classes. So this term again will become 0 by the virtue that the time interval from all the paths is 0. So how it comes, you can see that this is uh, equation number 3, and you can write as delta q dot, or here we can write as d by dt delta q. Q is the coordinate. So no, as we know that, remember this equation number 3, uh, as we know that the time derivative of these two terms, curly L over curly q dot into delta q, it will, again, this is the product of two terms, and this is the derivative with respect to time. So the first term into derivative of the second term, which is delta q, and then the derivative of the first term into second term. So remember this equation, and here we can rearranging this equation to obtain equation number 4. So replacing the second term in the right hand side of equation number 3 by equation number 4. So in 4, in fact, we have to replace this equation. This is the second term in the equation number 3. And for this, we can write this term. You can see this term and this term are same. So putting these terms for this, we can say that the equation becomes delta L is equal to curly L over curly q into delta q plus d by dt curly L over curly q dot into delta q minus d by dt curly L over curly q dot into delta q. Now, taking delta q from these two terms, from this term and from this term, and rearranging, so we can get uh, this equation. No, putting equation number 5, this equation in the equation number 2 for delta L, which is the basically the Hamilton principle. So if we put this whole equation number 5 in equation number 2, so we have two terms, and the first terms will become 0 as delta q is same for T1 and T2. The first term vanishes as delta q is same at T1 and T2. So what happens? We are left with these terms, and these terms can be reduced when the derivative, the integral is 0. It means that as delta q cannot be 0, so it means that this coefficient must be 0. So we are left with these terms, and in fact, this is the Lagrangian equation of motion. D by dt curly L over curly q dot minus curly L over curly q is equal to 0. So we have derived the Lagrangian equation of motion, where L is the Lagrangian function, which is equal to t minus u, and it can be used for different physical problems. So all this is for today, and we can do some more related topics to the Hamilton and Lagrangian formalism in the coming classes. Okay, so thank you very much.